Well, good afternoon, everyone. Welcome to our special panel session on the topic, the role of foundational studies in mathematics. So the format this afternoon is as follows. I will invite each of the panelists to speak for about 10 minutes. And then after that, there will be a discussion among the panelists. And then following that, we will invite the audience to ask questions to any one of the three panelists. Before we start, let me just briefly and quickly introduce our three distinguished guests here. I think many of you will know them already, especially those who are attending this logic summer school. So from right to left, Professor Hugh Woodin of Harvard University. He's professor of philosophy and mathematics at Harvard University. Hugh Woodin graduated from with PhD from Berkeley, and he was professor at California Institute of Technology, and then UC Berkeley, and then currently at Harvard University. I should also say that he was already full professor at Caltech before he got his PhD. So that is a bit in the wrong order, right? Professor Gus MacIntyre, Emeritus Professor at Queen Mary College, University of London. He was formerly professor at Yale University and also at the University of Oxford. And I got to know him very briefly when I was a graduate student there, but then I left, and then he was at Yale. And after Oxford, he retired from Oxford in 1999, and then was a professor at Edinburgh, and then later at Queen Mary University. I should also say that Professor Woodin is a specialist, a world authority in set theory. Professor MacIntyre is one of the foremost experts in the field of model theory with applications to algebraic geometry and number theory. And lastly, Professor Ted Slaman, University of California. Gus MacIntyre got his PhD under Paul Cohen at Stanford University. Ted Slaman. Dana Scott officially.
I worked with Paul Cohen.
Worked with Paul Cohen, okay. I stand corrected. Professor Slaman received his PhD under Gerald Sachs at Harvard University, and he was professor at the University of Chicago before he joined UC Berkeley in 1995. Professor Slaman is, again, one of the leading experts, or maybe the leading experts in recursion theory, and recently with additional interest in applications of recursion theory to Diophantine approximations and analytic number theory. So to start, may I invite Professor Gus MacIntyre to give you his opening remarks. Please welcome Professor MacIntyre.
Well, thank you very much. I've taken part in such things before. I don't have particularly happy memories of them, but let's try to do better. I think it's probably best for me to begin on a sort of autobiographical note and touch on certain things which I've liked and certain things I haven't liked, and then we can discuss around them. I'm particularly happy to be at this panel with these two very old friends and very esteemed friends. So I grew up in Scotland in a rural area. There were no mathematicians or philosophers in my family, but we had an extremely good educational system, excellent libraries, excellent facilities for getting difficult things from libraries. And I was somewhat precocious. I went very early to primary school and jumped classes and so on. So by the time I was a young teenager, I was reading very widely, and I suppose via things like Bertrand Russell, Essays on Logic and Knowledge, I got in and learned about mathematical logic, and I found it very fascinating and somewhat easy to get started trying to do things. And of course, I was very fascinated by Gödel's work and by set theory in general. And I was already doing some slightly original things as a fairly young teenager, but I didn't really intend to be a philosopher. I was fascinated by these things. I didn't intend to be a mathematician. I intended to be a writer. And I applied to university when I was young, and I said I was going to do literature, but the system in Scotland allowed you to change the document at the last minute, and I changed it to do mathematics and astronomy. So I did 2 years of that, and I did some radio astronomy and so on. And in the meantime, I was buying a lot of books that seemed to be cheap at the time, and I started reading serious things in mathematical logic, and I became fascinated by set theory. Then when I left Glasgow after 2 years because the logic there seemed to me to be straight from the Middle Ages. You know, it only just got beyond the syllogism, and I knew a lot. But I was taught by very, very good mathematicians. Rankin, who was a very world-famous mathematician. I went to St Andrews, where they had a math philosophy degree, and again I had the good fortune to meet good mathematicians and good philosophers, quite inspiring people. I also had the advantage that I had access all hours of the day and night to the university library, because the librarian had been at school with my father in this remote town on the west coast of Scotland. And there I began to read serious things like Mostovsky's books and so on. So I was much more interested in logic, but I was very much interested in philosophy. I thought a great deal about it. I did half philosophy courses, and it was half math, half philosophy. I did well in them, and I was persuaded to go to Cambridge to do philosophy. This I do regret now. I could have gone, I guess I could have gone to the States already at that point, although I was very young. I did 2 years at Trinity College, Cambridge, which is the elite UK educational place. I did very well in philosophy, but looking back on it now, it seems to me as if I was living in some kind of comedy film. Things that were being discussed. They seemed utterly unrealistic to me. But I went to mathematics courses as well, just for relaxation. Then I went to Stanford, largely because I had heard about Paul Cohen, and also because I had read things of Dana Scott and Kreisel and so on. I could have gone to Berkeley and some other places, but I chose to go to Stanford. This fact has been held against me even in recent years by John Addison at Berkeley. They know that I didn't come to Berkeley. I went to Stanford instead, and they don't seem to understand why. At the time, it was Cohen. It was new and so on, and it fascinated me, and I tried to read it on my own. And so I went to the philosophy department at Stanford. There was no real distinction between math and philosophy there, and I worked with Dana Scott, who was a fantastic supervisor. But after a couple of weeks, I decided I couldn't stay in the philosophy department. I already didn't like what I was hearing, but I liked the math courses I was doing. And in those days, at least, it was easy to move. I went to Patrick Supes and said I needed to leave, and he just said, well, just go over to the math department, we'll send the money after you, or something like that. And I went over there and I did a PhD very rapidly. I was offered a job in the philosophy department by Lakatos, I met at Stanford. But once I started seriously on the mathematics again, I found that my many years of reading in philosophy had no influence on me at all. Most of it meant nothing. You know, most of the people I read who were writing about philosophy of mathematics might as well have been talking about the philosophy of bookkeeping or something. There was nothing specific to mathematics in it. My interest in set theory remained. I had some marvelous courses at Stanford in set theory from Ezra Levy, and I had close contacts with Paul Cohen, and Dana Scott was a marvelous supervisor. I met Solovey at this time. But gradually, things I had learned in the remoter past about algebraic number theory began to intrude, and I wanted to try and use what I knew in logic to interact with algebra and algebraic geometry and so Now, that was not particularly congenial to any of the people in the logic group at Stanford at that time. But Dana was a very helpful supervisor. He introduced me to Abraham Robinson, and I found him very, very congenial. It was a very primitive time for logic applied to number theory, but I felt it was going to blossom. And the teaching at Stanford in so many areas was so fantastic. I learned from many mathematicians things which I was within a year or two able to use in model theory. But I have to say that overall my feeling is, well, the one great event for me at Stanford was meeting Kreisel, who was indubitably the greatest influence in my life, my intellectual life. Some of you may have met him, I don't know, but he was a very difficult personality who generally fought with every friend he ever had. But with him, I spoke on the phone twice a week, and some weeks received, well, some days I received 5 letters from him. And they were about everything, but frequently they were about very specific lines in some recent paper by somebody with philosophical pretensions. And these pretensions didn't survive very long when Kreisel got going. Of course, he was a close friend of Wittgenstein. He had been at Trinity, and he determined my philosophical life insofar as it exists, but it's left me with no taste whatsoever for any organized philosophical activity relating to logic. And I suppose we may be expected to talk here about foundational crises and things of this kind. For me, there is no foundational crisis. And there hasn't been for a very long time. And under the influence of Kreisel, I tend to regard the earlier crises around Russell and so on as overblown. People made too much drama out of them, and they gradually just faded away. That's probably enough for me to say just now. I would like to say that I love set theory. Many people think that I'm an enemy of set theory, and I love recursion theory. I've dabbled in both. These are the real thing for me, but it would take a lot to persuade me that there's very much serious philosophy of mathematics going around, in the sense that it's got very much to do with the way mathematics evolves and has evolved.
Okay, thank you. Professor Slaman?
Oh, thanks. Thanks, CT. It's funny, Angus started with some memories. I'll add one. There's a lot of serendipity in mathematical life. And when I was an undergraduate, at Penn State, and my degree was in physics. But I found, in my last year or two at university, my interest gradually, I realized what I really liked about physics was math. And so I decided I was going to leave the sciences and move into just pure math. And I applied to graduate school, and I got into various places. And it came down to either going to Harvard, which is where I went, or going to Yale. And it's because of Steve Simpson that I ended up in recursion theory instead of model theory. So small effects small forces can have major effects in your intellectual life. So about foundations and the role of foundations in mathematics. I confessed to Hugh yesterday. I said, I don't know what I'm going to talk about in this panel discussion, because this was yesterday afternoon, I don't really have an explicit, well-formulated and defensible position on the role on foundations of math. So Hugh looked at me and he gave me, just looked like that, basically. He gave me this kind of sardonic smile, and he said to me, well, you have 12 hours to think of one. So I thought that was a little harsh. Yeah, but seeing that it was 4 o'clock in the afternoon when he said it, And he gave me, I said I had 12 hours to think of it. I realized it wasn't as bad as I thought because he was giving me time to eat and to sleep and to do other things. You know, so he was being generous. It didn't demand that I do it, get a perfect one, spending all my time on it. So I did take it to heart, and I spent the rest of the day and some time this morning before the lecture started, thinking about it. And, what is it that I really think about foundations of math and the way that foundations gives insight into mathematical practice? So I truly have not tried to distill an explicit philosophy of math, but I do operationally have an implicit way of behaving. And so that's what I think, that's about all I can report on. So I see foundations, there's two kinds of foundations in math. One is, I think, common mathematical practice. You have some emerging mathematical subjects, some piece of a mathematical investigation. And initially it starts out intuitive. Right? And you can be working on mathematical things without actually, you're exploring a mathematical phenomena. And then there's a foundational effort that goes into saying, what is it that we're talking about? What are the primitives of the area that we are investigating? What are the basic constituents of this area? And we know a lot of examples, but what are the essential ingredients? Right? And then giving those essential ingredients, pulling them out, isolating the properties which distinguish them from other mathematical situations, and arranging the subjects so that you've made everything very efficient because you're working with the heart at the heart of the matter. Right? That's foundational. It doesn't necessarily have to do with mathematical logic. It depends on the area in which you're working. Getting the math together so that's like measure theory. Right? What does size mean? Right? So what does extent mean? Those kinds of things were great triumphs in math, and I think that they qualify as being foundational. Right? So there's that. There's the aspect that is most familiar to me, which is the other aspect of foundational, is the part that one experiences as a mathematical logician. So I think when metamathematical considerations come into play, there is a foundational aspect to that too, whenever that happens. Now my experiences, my training, and my perspective as a mathematical logician is recursion theoretic. And in recursion theory, it's the ingredients of definability, or the ingredients of the sorts of constructions that you can use, the complexity of the objects that you employ. What are the ingredients that you bring to bear on some problem? And the recursion theoretic analysis is typically those ingredients will allow you to analyze problems of this complexity and no further. It sets the boundary on what the mathematical means you are employing can achieve. Like such and such theory is decidable. It can be computed by algorithm. Yes, there's a good example. So first there's the logical aspect of saying such and such mathematical situation can be algorithmically determined, like the decidability of a theory. That's one kind of foundational investigation from the point of view of involving metamathematics, because you're analyzing what computations mean and seeing the limit of what they can accomplish. The other kind of foundational activity would be to specify what is an algorithm. Not what is a program, not what is a computable function, but what is an algorithm. And how do you identify that two programs are using exactly the same algorithm? Right? So the sort of precise definition of algorithm is yet, I think, to be satisfactorily accounted for. Okay, so there's the now if you're thinking about recursion theory. So I gave an example where recursion theory lets you distinguish between things that are decidable or undecidable. It also lets you distinguish between when certain statements can be proven finalistically or require something beyond the usual finalistic methodology. Right? So the best example I know, the canonical example, is the Paris-Harrington theorem. And as a side, Harrington, who's done work on models of arithmetic and recursion theory and set theory, model theory, he once told me he never understood set theory and he never understood model theory. Everything he ever did was recursion theory. And it's because also he's a genius. So he could have been working with he could have been working with 2 water bottles and a peanut, and he could have proven those theorems. So it's recursion theory gives you this kind of meta-mathematical analysis. I'll give you another example of where something that's, you could say, is foundational gives you mathematical insight. Suppose you've analyzed some situation. You proved a theorem. Here's a complicated situation, like under what circumstances is a theory omega categorical? Okay, so there's a beautiful theorem representing how many types you have for each number of variables. So and then you could ask, well, is there a better characterization? Is there yet a simpler criteria to tell whether a theory is omega categorical? Right, there's a beautiful one. All the countable models are isomorphic. That sounds like it's 2 quantifiers over the reals, but then you get something about the theory, right, which is arithmetic. Could you have an even better characterization? How are you going to prove that there's no simpler characterization of that property of a theory? Well, you have to show that it's complete at the level of the definition at the level of the criteria that you already have. So you can prove that you can show that certain analyses, mathematical analyses, are optimal. You can show that certain set of tools are inadequate. You can make precise the notion of, well, here's some proof that brings in all kinds of machinery. Is there an elementary proof? Right? That question is made precise. That's a foundational question in my mind. But you have to define what it means to be elementary in order to say, yes, there is one, and more interestingly, no, there is no elementary proof of this fact. Right, so formulating those kinds of questions involves understanding, having a mathematical grip on a meta-mathematical investigation. And I think that getting those precise answers in mathematical terms to meta-mathematical questions sheds a lot of light on the nature of math. I'll end with that.
Well, I was an undergraduate at Caltech, and I started out in analysis. I loved analysis. And I was given as a summer research project Kaplansky's conjecture, which turns out to be independent. And so that's why I ended up in set theory. So then I was a graduate student at Berkeley. So on the role of philosophy in mathematics or foundational issues, I agree with Angus. I think the original role of set theory in foundations is obsolete. We understand the basic notions that set theory was designed to clarify. But there's a serious foundational issue for me now in set theory, and therefore also in mathematics, and that has to do with all of the independence phenomena. So we have the conception of the universe of sets, and if that conception is meaningful, it would seem to demand answers to questions like the continuum hypothesis. And that's clearly a foundational issue, because what does an answer mean? You can just assume it. So what criteria, what's that, how do you analyze that investigation? And how do you make the case one way or the other? I mean, Cohen, at least the last time I spoke to them, felt that the independence of the formal independence of CH from the ZFC axioms was the last word on the matter. That's independent. Well, to me, that's maybe not the last word. There are other questions which are independent, which in some sense have answers. Determinacy provides a good example of that. So the basic questions about the projective sets, not in the algebraic geometric sense, but simple sets of real numbers. Just look at closed open sets under continuous images and complements. Those are the projective sets. And what can you say about them? Are they Lebesgue measurable? Do you have selection principles for projective subsets of the plane? Those are all independent. But determinacy gives the answer, and the entanglement with determinacy with large cardinals is a powerful case. Those are the correct answers. So in some sense, what's happened is we now have the correct axioms for second-order number theory. ZFC axioms don't give full information to second-order number theory. Second-order number theory is the theory of the integers with all sets of integers. And projective determinacy is arguably the correct theory for that structure, much as the piano axioms are the correct theory for arithmetic. So now the question becomes, can one expand that understanding to V itself? Or can one make a case that there can be no such expansion? And that to me is a foundational issue. And the answer, whatever that answer is going to involve some philosophical issues. And there could be a dynamic there. So those are the issues that I'm very much interested in. Now you could just say there are no answers there. Maybe Cohen was right. Ignore the determinacy success. But then you have another issue to deal with. The conception of the universe of sets with large cardinals makes the prediction that those large cardinal notions are consistent. Now, whatever your view on mathematical truth is, the consistency of a theory is a meaningful statement. It's an arithmetic statement. It's a pi01 sentence. Now, you could take the view that it's not interesting, but that doesn't mean it's not meaningful. And so it's an interesting fact that to date, at least as far as I'm aware, no one has been able to make a credible argument for the consistency of large cardinal axioms, except for the conception of the universe of sets in which those large cardinals or something like them exist. So that's interesting. Why can't there be another way of verifying consistency? So if it is in the conception of the universe of sets, and that is how you verify consistency, existence gives you consistency, then you can't leave CH as indeterminate. It makes no sense to have a conception of the universe of sets with large cardinals and give up on questions about small sets. So there's a challenge there. So what should the correct view of truth in set theory be? And that's, to me, a genuine foundational issue. Whether it is relevant to other areas of mathematics, well, who's to say? We've only been doing mathematics for a few thousand years. In 1,000,000 years, set theory will be the same age as number theory, and hopefully connections will have been found. So anyway, the independence in set theory, the ubiquity of unsolvable problems in set theory, is a serious philosophical issue to me in the very conception of the universe of sets. And how does one deal with that? Good. I think I used my 10 minutes.
Oh, so we have some discussion on the ideas or on the thoughts of the panelists. Does anyone add something?
But what you just said, I mean, well, philosophical or not, this is a gigantic problem of our understanding of mathematics. I mean, I certainly deeply attached to set theory. I don't think on a daily basis about these consistency questions because my brain is not equipped to do so. I would go mad if I started to think about this the whole time. But you've obviously spent a lifetime and gone amazingly far on these things. Are there possible solutions which you've seen and discarded of this? I mean, what did Cohen say apart from saying that he had?
So I'll describe my first time I gave a talk at Stanford. I went to Berkeley in '89, but I didn't give a talk at Stanford until around 2000. And at that time, so the nice thing about an unsolvable problem is you can change your mind. So at that time, I had decided maybe CH was false because there was a candidate axiom that was settled the theory of P omega 1 in as robust a way as projective determinacy settles the theory of second order number theory. And so I was going to Stanford to give a talk on that. That's, I presume, why I was asked. So I looked at Cohen's book. I said, I better read up on what he said. And so I read at the back of the book, set theory and the continuum hypothesis. And there's a phrase as something like, it's speculated that eventually it will become to be accepted that CH is false. So I gave my talk, and Cohen stands up and says, well, I just want everyone to know that CH is independent, has no answer, and that's the last word on it. And so then I said, well, wait a minute, that's not what you said in your book, or wrote in your book. You said that you thought CH was false. And I should have known better. And Cohen said, no, that's not what I said. I said, I think it will eventually become accepted that CH is false. I did not say that I thought CH was false. So at that time, and based on my later conversations with Cohen, I had a very long conversation with him in Vienna at the Cardinal meeting. He was a formalist. He thought everything was independent. He speculated that, Goldbach's conjecture was independent because you're mixing the additive and multiplicative notions of integers. He literally said that. Anyway, that was his view. And I don't know what his view was in the 60s when he discovered forcing. Forcing axioms was an appealing route and for not CH, but in the end, I felt compelled to move away from that. And the trouble is, it wasn't fitting into a framework for a theory of V. Having a solution to CH, to me, it can't just be CA or CH. You have to have a global theory of V. And so there are not many candidates for a global theory of V. And, it's kind of, you could just play the logic game. The axiom V equals L is a robust axiom. Very hard to get independence from that axiom. Shalat has a nice phrase. It's a semi-complete axiom. But it's false because it denies large cardinals. So you could ask the logical question, is there a semi-complete axiom for V which is compatible with all large cardinals? And how would you verify that? Well, that's something you can investigate. On the consistency question, there is another, twice I've been on panels like this, more than that, but there was one in Munich, the Russell meeting, and Pfefferman was in the audience. Pfefferman was a set theoretic skeptic. And so in the course of the discussion, I asked Pfefferman, is PD consistent? And he said yes. And then I said, how can you believe it's consistent if you don't think it's true? And he said, well, if it was inconsistent, you people are all very smart. You would have found the inconsistency. Okay? Now, it's funny because I had exactly the same conversation with Jensen. I asked Jensen, is PD consistent? This was at Oberwolfach, and he said yes. And I said, how can you believe it's consistent if you don't think it's true? Same answer. So it does raise an interesting question. You look at determinacy axioms, and you look at large cardinal axioms, there's a certain almost syntax that is used to formulate those axioms. Some have been formulated that do lead to a contradiction, but that contradiction's never been difficult. Why? There are difficult theorems in set theory. Every theorem is a proof that something's inconsistent, namely the negation of the theorem. But why is it that the large cardinal axioms that have been proposed and fallen, the determinacy axioms that have been proposed and fallen, and there are not many of those, why isn't there a deep structural proof of inconsistency? And I think that's what was lying behind intuition, maybe even Jensen's intuition. So that's an interesting question. And it comes back to the consistency claims. How is it that, is there any way of justifying the consistency claims? Why is CFC consistent? If you're a set theoretic skeptic, you have no basis to believe in the consistency of CFC. There's no universe. Presumably, the belief in the consistency of arithmetic, it traces back to the strongly held view that the conception of the integers is a coherent conception. But you can't really make that case as powerfully for set theory because of all the independence results. So, to a set theoretic skeptic, why is set theory consistent? Why are measurable cardinals consistent? Why are supercompact cardinals consistent? Are they consistent? So, and how could you, is there a way of authenticating the consistency of those notions that doesn't trace back to a conception of the universe of sets? And this is a real difference. I get asked a lot about category theory. Why? McLean and I used to debate. I would visit Ted in Chicago, and somehow we have these discussions. And
He liked to talk.
what?
He liked to talk.
And so, McLean strongly felt that the categorical framework was an appropriate framework for a lot of mathematics. But it's interesting. Category theory can interpret set theory, so it can interpret large cardinal axioms. It has never discovered a large cardinal axiom. Why?
I mean, this is also something which is influenced. I mean, of course, category theory is nowadays developed to an enormously sophisticated level, these sometimes luring, but the people who are doing category theory, geometry, they never use, in fact, arguments of set theoretic type. I mean, they don't use any kind of transfinite recursion. Some of them might use a Zorn's lemma thing or something, but they don't. They're not in the same games.
Yeah. So why isn't if category theory is the correct framework for mathematics, then mathematical knowledge discovered in set theory should be rediscovered, shouldn't it? Okay. In this correct framework.
See, this I don't know. I mean,
Well, then why is it the correct
I don't
framework?
think it is the correct. I mean, I don't think. I mean, I certainly like category theory very much. And I spent a lot of time with it. I used to tell I don't and I think it's a very appropriate foundation for all of mathematics, but for some very important parts of mathematics, physics. But it doesn't seem to me that you're right. Of course, it can do something, it can do set theory, but it doesn't do. For some reason, it doesn't do the kind of mathematics. It simply omits much of the kind of mathematics that set theories do. I mean, for example, I was quite close to Quillen. He was at Oxford, and he was a great and very imaginative mathematician. I used to go to all his lectures. I remember being at one of them when he did an argument, which was perfectly intelligible, and he finished very proudly saying, I don't think this argument can be formulated. It was absolutely clear. I'm not saying it's a clear set for that, but it would have done it no good to formulate. I think that this issue between category theory and the set theory is so tricky. The set theory is, the category theory is very important, obviously, for a certain range of mathematics, and some of the practitioners have no desire to go for it. It's just someone not in their mathematical genius that they go any further. I think it's important to think of foundations maybe for different parts of them. Maybe we have too grandiose an ambition of making a foundation for all of them.
Yeah, no, I was just making the point that the discovery of the hierarchy of large cardinals, which is a hierarchy of consistency strength, seems to be unique to set theory. That's all. And so one can speculate, why doesn't that hierarchy, why hasn't it emerged in other areas? That's all. I'm not making a judgment. I'm just pointing out that this is my response to McLean, that it is curious that category theory hasn't discovered its own strong principles. It borrows them from set theory, right? But it hasn't discovered its own. It's not saying anything negative about category theory. It's just saying that if the large cardinal hierarchy is so intrinsic, one could wonder why hasn't it merged in other areas of mathematics. I don't know.
I'd like to say something about the hierarchy, which is one thing that really that I find very compelling about let's say a distinguished conception of set, is the idea that there's a hierarchy of complexity, a hierarchy of definability, hierarchy of strength, and it's not only is it one-dimensional, but it's well-ordered, right? And it's reflected in the wage hierarchy, in Steele's theorem about uniformly degree invariant functions, in the consistency strength hierarchy. That fact that there's this one way to go, and things seem to fit it. Things seem to be measured by it in one metric, needs explanation. But to me, that's an astounding fact. If there's so much independence, why is it that so many things are comparable? And things that did not come from the same sources of mathematical investigation.
This goes on. This interests me too. I mean, when you was talking, I mean, this is in light of what's just been said. I'm almost asking you for a thought experiment. And suppose you had two utterly coherent conceptions of V, which clashed. I mean, we don't. What would you then do to try to decide what you would go for?
Yeah, that's like saying, what would I do if large cardinals were inconsistent, for example. I mean, it's counterfactual. This almost happens in what's going on now in set theory. My view, set theory is at a critical junction. It faces two very different futures depending on certain technical conjectures and whether there's an ultimate version of that. And up to about 3 years ago, it looked like there were going to be two different versions, kind of a flavor A and a flavor B, which in that view would have led exactly to the dilemma that you described, where you have two maybe semi-complete axioms, to borrow that phrase again, but which are incompatible. And that really looked like it was going to be the case. And it turned out not to be. Only one flavor can survive, if it indeed can reach all levels. So, so it's hard to answer your
No. It is a very fun thought experiment. I'm just curious as to how you might.
I mean, I would say if it happens, then that challenges the very conception of phi, because it shouldn't happen. It would be like an inconsistency result. But I mean, the other thing that could happen is there's another way to explain the large cardinal hierarchy. Maybe not sets, but it hasn't happened yet. So one could speculate that. What if, someone came up with a theory of widgets, and here are the axioms for widgets, and lo and behold, they're large widgets. The existence of large widgets captures large cardinal hierarchy. I mean, so, I don't know. I mean, you could ask whether the large cardinals are relevant to the so-called core problems of mathematics. That's less of an issue to me.
How about to you, Angus?
It's also, I mean, I like this idea of long. I'm just thinking about that. Because this is very slow to mathematicians in the future. We certainly at the moment, except perhaps just analysis, the large cardinals will impact on geometry and novelty. Well, we have no clues as to what might happen. But it doesn't seem to be unlikely to happen, but it's something that I can research for you.
I don't know enough about it.
How can you rule it out? I mean, I personally feel like math set theory is like really incredible. Certainly for any mathematician. And it's the mere fact that at the moment its methods are to a large extent isolated from the rest of mathematics is nothing. It's more beautiful than any person like that.
Well,
and it appears to be consistent.
You're being very charitable to set theory. I think set theory has a serious issue out of the independence. The trouble in set theory is you write down a statement about the uncountable, and very likely it's independent. How do you build a mathematical structure theory in that situation? All you can do is generate a theory of possibility. But that's not a structure theory. That's the model theory of set theory. And to me, the model theory of set theory is a different subject than set theory. And it's the model theory of set theory that has been the primary focus of set theory since Cohen, because the technique for independence is so powerful, and there are many, exploring the landscape. So I don't think set theory or transfinite mathematics has really had a chance yet, because there's no setting in which to do it because of the independence. So maybe if there is such a setting, and it really has a chance to develop a rich structure theory, who's to say what will happen? So that's part of this, the issue that's facing set theory now. So I'm probably the only person who holds this view. There's certainly a view among set theorists that want to think that the model theory of set theory is set theory. But I don't hold that view. That's like, there are questions, there are very difficult questions in the model theory of set theory. But they're not questions about V. Like, I'll give you an example. Suppose you have a sentence in the language of set theory. And suppose there are well-founded models of ZFC plus phi. Suppose for every alpha, there's at most one model of height alpha. Suppose that there are omega-1 many models, different heights. Does that sentence imply V equals L? And you have to be a little bit careful. You can come up with trivial counterexamples. So you could ask the first question. Suppose you had a sentence phi in the language of set theory, and it has exactly one well-founded model. Does that model think V is equal to L? And the answer is no. There's a counterexample. A student of Harrington did that. So that's part of this model theory of set theory, and these are hard questions. But they're not V questions. The spectrum problem for well-founded models of set theory is a really difficult question.
What's the spectrum?
Well, it's like counting models.
Nice.
Like, and you can get kind of silly insight. Like, suppose you have a complete theory in the language of set theory, and it has countably many well-founded models, but no more. Okay? What can you conclude? That theory, it's a complete theory. V is equal to Hod is in that theory. That theory, you can limit the large cardinals that can be present. So it's constraining the model. But those are not V questions. Those are questions in the model theory of set theory. And there are many, many questions like that, and some of them are incredibly difficult, or seem to be, but they're not V questions. So I think a challenge for set theory is to figure out what V is, and then if you can do that, try to develop true transfinite mathematics if that can be done.
What do you think is evidence in this investigation? How are you going to acquire evidence that V has a certain
description? I don't want to dominate this discussion, but large cardinals seem to be the clue. Large cardinals are orthogonal to forcing, in the sense that the more large cardinals you have in V, the more immune V is to forcing. And there have been some recent theorems of the last few years which are quite surprising. And these are theorems, the picture that's emerging is almost that large cardinals are trying to tell you that some version of V is equal to L by proving the best So this begins with Solovey's theorem from supercompact. If V is something like L, the GCH should hold. But no large cardinal can apply the GCH. But wait a minute, if you have a supercompact cardinal, the singular cardinals hypothesis holds above the supercompact. The best possible result you can hope for. And then I'll give another example. I'll give two more examples. Another a feature of L is not a generic extension. Do large cardinals give any insight into that question? So first of all, is that even first order? Well, it turns out that if V is a generic extension of an inner model, that inner model is sigma 2 definable from parameters uniformly. So V can talk about the inner models of V that it's a generic extension of. So you can do the theory of that. And make a long story short, there's the Usuba theorem of about 2 years ago. If you have an extendable cardinal, which is stronger than supercompact, and you look at all the inner models that V is a generic extension of, there's at least one. That's exactly the kind of thing you would expect. Now, you can't prove that from supercompact. It's false. You have to ramp up the large cardinals, and then you get more evidence. And then the last bit of evidence, and I'll just end with it, another feature of L is V is equal to Hod. Now, Hod is the hereditarily ordinal definable sets introduced by Gödel. When I was a graduate student in Los Angeles, or afterwards in Los Angeles, when I was at Caltech, there was the cabal studying determinism. And the idea that V is equal to Hod was kind of universally rejected. V should not be Hod. Now, I've always found that a kind of weird situation, because it's like the argument against the axiom of choice. You say the reals can be well ordered. Show me a well ordering of the reals. All right. If every real is in Hod, I can show you a well ordering of the reals. So you show me a real that's not in Hod. You know, it's just anyway. So what's where does Hod enter the picture? Again, with an extendable cardinal. So if you have an extendable cardinal, there is something called the Hod dichotomy theorem, which should have been proved in the 70s, but wasn't. And it says that either V is extremely close to Hod, in the sense that all sufficiently large singular cardinals are identified as singular in Hod, and their successors are correctly computed, and much, much more. Or V is extremely far from Hod in a way that we don't know how to force. So this raises the speculation that it's not a dichotomy theorem. That V must be close to Hod if you have large cardinals. But wait a minute, that's another confirmation of it saying V is close to definability. It's exactly what V as an L-like model would predict. So there seems to be this emerging picture that you bring in stronger and stronger large cardinal notions. They are they're making forcing powerless. Because forcing above a supercompact or an extendable cardinal and preserving the cardinal is extremely difficult. Most of the techniques that we use to generate pathologies, you can't do that forcing. And these theorems, like the dichotomy theorem and the others, are symptoms of that. So, yeah, so there's evidence emerging, perhaps, that something like a V as an ultimate L is true. Now you need the axiom, and then you need to know that there's no Scott's theorem, right? And well, we have the axiom, or the conjectured axiom, and we have the conjecture, the ultimate L conjecture, which would confirm there's no Scott's theorem. Okay, but we don't know which way it's going to go. In other words, it's clear in a certain perspective there is an ultimate L. But that could be the ultimate L, could simply be that's as far as a certain kind of analysis of large cardinals goes. And that there's a level of the large cardinal hierarchy that it cannot reach. So it's ultimate, but only for a certain kind of analysis. That would be the dark future. Now the other way, it could be ultimate because it is genuinely an ultimate L, and it captures all large cardinals. Well, V is ultimate L, the formal axiom implies V is not a generic extension. So if you think of V as having a width and height, it binds the width to the height. Forcing is now powerless, because forcing changes width, preserving height. And so in a context of an axiom like V is ultimate L, there's no independence by forcing. The only ambiguity in V is the height, large cardinals. And so that opens the possibility for developing a rich structure theory, which we haven't really had the axiomatic setting to do that. But again, it could go the other way. So yes, there could be evidence, but we don't know. I mean, the idea of an ultimate L seemed ridiculous 10 years ago. But that's because there were fundamental misconceptions about the nature of these inner models. And they were, there was a misconception that seemed to convincingly predict there could be no ultimate L that you could build. Hence, there is no ultimate L. It's just an endless thing, endless road. But that was based on an assumption that turned out not to be correct. So that's where we are.
Well, perhaps I think this is a good time to invite the audience to come up with questions. Maybe I can start with the first one. So assuming that everything goes according to plan, we do have ultimate L, and it's accepted as the right model to have, or the right structure to have. Does it mean the end of set theory?
Okay, I'll make two comments. If the ultimate L conjecture is true, then the real debate begins. Is the ultimate L? Let's suppose that there is some kind of mass hypnosis for the set theorists, and they all embrace ultimate L, which they will not. Is it the end of set theory? No, I think it's the beginning of set theory. Because you'll have an opportunity to develop, you'll be free of independence. You'll be able, you can start developing through the lens of ultimate L. You will see patterns that you do not otherwise see. I'll give you one example, and then I will shut up. Determinacy is often studied, and if you if you look at large cardinals, and you look at you can form the smallest inner model of V containing the reals. That's called L of R. And if you have infinitely many Woodin cardinals, or with a measurable above, so say a proper class, then the axiom of determinacy holds in this minimal model, containing all the ordinals and the reals, and you get a very rich structure theory. But is AD L of R, that's the assertion that this determinacy axiom holds, true, or do you need to resort to the large cardinals? Okay, well, let's take another proposition. If you're going to ask about the axiom of choice, you want to know how simple of a well-ordering of the reals can there be? Is there a well-ordering of the reals in L of R, for example? Well, no, if the axiom of determinacy holds. So we have two propositions. The axiom of determinacy holds in L of R. Maybe just the axiom of choice fails. Now, there is no connection between these except for the obvious one in ZFC. In Cohen's model for not CH, the axiom of choice fails in L of R. Right? So there's no strength in the axiom of choice failing in L of R. But now, look at that through the lens of I'm an L-like model. So throw out all the universes except in this hierarchy of approximate generalizations of L. And now in that very confined setting, through that very narrow lens, ask the L of R question. And Steele showed that the axiom of choice fails in L of R in that setting if and only if determinacy holds. So now you have a completely different perspective on why the axiom of determinacy holds in L of R. It's just simply L of R is unable to compute the well-ordering of the reals. So in the ultimate L setting, this might be the pattern, that there are roots to new hierarchy, new strong principles that aren't formulated in the language that we use to describe large cardinals now. They're going to be formulated in terms of complexity. And without the confined setting of something like V is ultimate L, you won't see the patterns that emerge. So that will be an issue. Will that happen? And if it does, and new principles of infinity come out of that analysis, then I think that starts to make the case for V is ultimate L. If the route to discovery of strong principles past the principles we know now is in the setting of ultimate L, then as a set theorist, that becomes compelling evidence for ultimate L. So, but that's a challenge for that picture. Even if you have the ultimate L conjecture and you're going to make the case for V is ultimate L, you have serious challenges because when you build in this picture of ultimate L, when you build this model, you're only using a supercompact cardinal. So why are two supercompact cardinals consistent? You're not using the second one. So there's a foundational challenge there. And how that plays out will affect how the axiom is viewed by set theorists. And it's too early to say. We don't even know if the axiom ultimate L is compatible with these large cardinals. That's the point of this of the ultimate L conjecture. So yeah, so it's hard to say at this point.
A question from the audience.
Mikhail.
I mean, if I can only ask one question, I will start with, because I have more. I will start with one to Professor Slaman. You gave examples of mathematical analysis of various pieces of mathematics. It seemed that these were examples of mathematical analysis of, in a sense, known piece of mathematics. So my question is, do you imagine that, can it be that foundational or logical analysis can lead to a genuine mathematical progress, in the following sense of genuine, that we can gather some mathematical understanding, but not mathematical understanding of a mathematical but not meta-mathematical phenomenon that is not understood otherwise? I don't know if the question is sharp enough, but can it be that logic can lead to a better theory of some non-meta-mathematical set of concepts and that wouldn't be understood otherwise? Are there known examples, or can there be, for example?
Yeah, so I think that, I'll interpret that question so that I can answer it. Okay, so in the way I want to. So I think I'm going to take the question as asking for an example of a meta-mathematically inspired understanding of some traditional mathematical phenomena, which led to insight about that phenomena, which then evolved our understanding and in particular produced results that were not meta-mathematically motivated. So I think that there's well, we've been hearing about the lectures this week of one such example. I'll tell you one that I know of for myself, because I was involved in it. This had to do with, CT mentioned I've recently been interested in questions of Diophantine approximation. So there, the sort of questions that caught my interest were questions about normality and approximation of transcendental numbers by rational numbers. So the question that we started out with was to understand the complexity of those phenomena, right? So it was an index set calculation. So this is joint work with Veronica Betcher and Jan Bougeot, ultimately. So there we wanted to understand, how is it that normality, which means that the digits are equally distributed asymptotically relative to a particular base, or relative to that all the blocks of digits are equally distributed asymptotically relative to representation in a certain base. So we were interested in studying what's the index set? How complicated is it? Is there a characterization of how complicated is it to tell about a real number that it is absolutely normal with regard to every base? Or how complicated is it to tell of a real number that it's normal relative to some base? And so that involved a recursion theoretic analysis of how the satisfaction of those properties evolves. How do the Skolem functions work? Right? Is there independence between realizing normality in this base and suspending normality in a different base? And there were results from the 50s and early 60s by Castles and Schmidt saying that the interaction between one base and another depended on a number theoretic property of multiplicative dependence. So two numbers are independent if they don't have any common powers. All right. So we investigated that. We figured out what was the recursion theoretic analysis? What was the index set? And in the course of that investigation, one has to understand how the Skolem functions work for the phenomena. And you have to have a complete understanding of it, because you have to show that if you're proving an index set theorem, you have to analyze to what extent those Skolem functions can behave generically, like the Skolem function. If you show something as sigma 04 complete, you have to show that the way that the sigma 04 property that you're showing is complete works can mimic any sigma 04 described situation. Okay, so then in order to do that sort of recursion theoretic investigation, we had to see how the satisfaction of the number theoretic property worked completely. And it exposed various dark corners in the way that things can happen. And that led to a characterization of exactly under what conditions for which sets of integers do there exist real numbers which are simply normal to exactly the elements of this given set and to no others. So it led to an extension of the Cassel-Schmidt theorem, right, in full generality, base by base. So it was a sort of meta-mathematical investigation, right, which revealed a sort of complete control over the way that things can be satisfied. So an exhaustive account of all the possibilities, which is what an index set theorem has to do. Right? So, and it exposed, possibilities that had not been articulated before, and then you could combine them to give a complete account, a finer account of what the transcendental number theorists had done earlier. So I think the answer is yes. I think that there's a kind of, in my experience, so what I know most about is a recursion theoretic perspective, which can be applied to topics other than purely recursion theoretic topics. And it's a certain point of view and a certain collection of ideas, but mostly the point of view is the relevant thing. What kind of understanding you have to understand it recursion theoretically. And then that has consequences. That understanding can lead to corollaries and applications.
Would other panel members like to respond to these questions?
Well, it's usually simpler than what they described, but I mean, the negative solution of Hilbert's standard problem, the mere fact that you could enumerate the primes as the positive values of unknown, unknown and inaccessible. Because they probably still don't have any method to give it to them. I mean, it didn't create a sensation. The fact that you could spell out unknown didn't in the end give you any detailed information for the primes, but the result was perfectly intelligible, could have been asked, and proof to a magician is utterly perspicuous. A small remark occurred in Putnam long before the soul But that's maybe too easy nowadays, but still, it was a big thing then. I can't remember the details. I wrote a paper once with Ken Hagen, the late Ken Hagen, on group theory, existentially enclosed groups and so on. And there was something there that impressed Graham Hickman very much. He was one of the leading group theorists. I mean, this result was purely group theory, but we usually made essentials in recursion. It happens, but you know, we have to go out and look for cases and then work pretty hard.
Also, let me just follow up on that last comment. I think that the attempt to go, so I think it's more interesting to take a certain mathematical perspective. Like you could say, well, there's the meta-mathematical perspective, there's the algebraic perspective, there's the geometric perspective. A certain mathematical, apply it to the things that are intrinsic to it.
We could take that perspective and apply it to other, think about other
math. But, you know, from the point of view that you've evolved in the way that you understand things. And then it will reveal those things that it shows in high relief, which, depending on different perspectives, make different things stand out. So it's more interesting to take the perspective you have and apply it to some mathematical thing about which you're curious, right? And then understand that thing as best you can, rather than I am going to go look for situations where I can. This is an implicit, I guess, criticism of some of our colleagues in logic, who go to look for independence results in a certain mathematical context, and they warp text to suit the independence phenomena. I think that's less interesting than to use the meta-mathematical point of view and try to understand what's happening there, whether you find independence or large cardinals or whatever you find.
Yeah, I mean, again, related examples which don't involve necessarily new mathematical results, but the use of meta-mathematics can greatly clarify what has happened. I mean, this was one of the early things that Kreisel did, and in response to this, Serre got the Fields Medal in 1954 for his work on homotopy groups, and like one or two other eminent French mathematicians, he's not entirely comfortable with the axiom of choice. I think on aesthetic grounds rather than anything deeper than that. But he made essential use in his work, which is complicated, he made essential use of various dualities in vector spaces and things of this kind, which would prima facie involve the axiom of choice. And he was not happy about this. He still took the Fields Medal, but Kreisel was at the Institute for Advanced Study at the same time as Serre, and Serre asked him, what on earth can I do about this? How do I get rid of the axiom of choice? And of course, if you just plunge in and look around and try to eliminate, you won't succeed. It's not easily. And on the other hand, Kreisel did it this way. He said, well, look, it's quite easy, much easier than most of says, but quite easy to see that the statements you're proving about the homotopy groups are arithmetical. It's also quite easy to see that the proof for which you get the Fields Medal is in ZFC, and then you can just pass into L and back out with absoluteness, and you've eliminated the use of the axiom of choice. So, and this was good news for Serre. He was happy with this. But it's sort of ad hoc. You have to interact with other mathematicians and get the idea there's something here that you might be able to bring logic to work on. That's it. If you go in with the idea that I'm going to change this field by using logic, you almost never get anything.
My question is actually about the role of the foundations of, or particularly the logical foundations of mathematics and the role of education in mathematics. For example, would something like a logic class, should that be held at the same level as the kind of quintessential algebra, analysis, topology sequence that typically grad students have?
I already had to respond first.
I think both, at least both you and Hugh should respond to this question because both of you had been chairs at Berkeley Math Department.
I think every graduate student should understand independence at some level. So I would think they should know some logic. You'll find as you become mathematicians and give talks, if you give a department colloquium, you can't assume that any knowledge of logic is known. So kind of hard to give a talk under those conditions. Whereas, it's an asymmetric situation, right? A number theorist comes in and gives their talk, and they assume what modular forms are and all of that. And I think independence, the fact that posed questions have been shown to be independent, and that there is a technology for doing that, I think that should be part of the basic knowledge that graduate students gain in mathematics. So I would, now obviously I'm biased, but...
I mean, you like logic?
I'm not saying that, satisfaction and structure and basic things like that should be part of the standard toolkit, whether you use it or not. And what everyone's view on logic, the incompleteness theorems are one of the great theorems of the modern mathematics. And they're not difficult theorems now. So why, people, I think, should have some knowledge of that. I think a professional mathematician should have some knowledge of that. So I strongly feel that they should have some knowledge.
I think if you don't know if you can't distinguish between something being computable and not being computable, then you're missing out on a huge piece of the understanding of modern math.
When I was at Yale, that was one of the nice surprises for me when I arrived, that the graduate logic course was compulsory for all graduate students. And there was a small student body at Yale, and very bright ones, and the majority of them went on to become professional mathematicians of considerable stature. So I taught a large number of very bright people, and they appeared to enjoy it. Some of them used the things later, and it also had occasional really nice side effects. On one occasion, a guy came in. I was teaching a course on stability theory, so it was quite advanced. A guy whom I didn't know before turned up, said he wanted to attend this course on stability theory. He was an engineer, so he misunderstood the content of it. But this guy went on to become a professor in Berkeley. He was by far the best student of the course. And there was another pre-med guy who just wanted to pass his time learning some logic. These guys, wizards, and they did everything. So, on the other hand, there was a compulsory course in logic at undergraduate level. I think Bethonie had insisted upon it with a general topology component. And Serge Lang, of course, was a very volatile, changeable individual. He, at one point, thought it was a good idea, but later on, he thought it was a bad idea. So we had a big ordeal in the math department as to whether or not every math student should do this material, very general topology, and logic. I think Serge was defeated in the vote in the department, but he never took no for an answer. He simply went down to the department office, asked the department secretary for the curriculum for the course, and tore it up and threw it in the newspaper basket. You know, there were strong views about these things. But later, he was very helpful to Van den Wees. We interacted a lot with him on some of the things I'm lecturing on this week. We learned from Lang.
Why did he have a negative opinion about Martin? What was it?
Well, he was probably writing some diatribe against something else at the time when he just needed to. And why? I don't know. I really don't know.
Any other questions?
Yeah, first one comment. So I think that set theory has really many, say, influence, or the model theory, set theory of other fields, because I came across when reading or hearing talks that also in topology or other fields there are suddenly open questions which they couldn't solve for 50 years or so, and then they found out they answer depends on the model of set theory one is using. So this is what I observed, so that there is indeed some impact in getting answers to questions where one didn't know what to do. And the other thing is, one question I have, do you see any parallels in the situation of set theory and computational complexity? Because in computational complexity there's also a big zoo of assumptions, and then people study how does this assumption imply those assumptions. There's only one big difference. In the model theory of set theory, if they show that two assumptions don't imply each other, it is absolute. In computational complexity, it is mostly, say, if these things are not equal, we can show that those things are not equal, but actually we don't know. Yeah, so, but do you see nevertheless a bit of parallel in this situation?
Well, parallel may be in this following sense, and I guess in complexity theory, when you can't solve the main problem, you study the kind of relationships. If you can't figure out that P is not NP, then you try to understand the basic landscape. In set theory, I don't know how strong the analogy is, but until you figured out what V is, you study the landscape of possibilities. But the difference is there's not a driving question. I mean, presumably, the question of P versus NP is not independent. We don't have an analogous question in set theory that we're headed, well, maybe the ultimate out, but that we're headed for. So there's a slight, it's not like in set theory, the community has a problem they can't solve, and so they're exploring the possibilities around what might happen in the attempt to solve that problem. That's how I naively interpret complexity theory. You have the main problem, P versus NP, and these are attempts at understanding that problem. But that's at a very naive level. And we don't have an analogous P versus NP question in set theory. It's not like the community is striving to answer a question that's well articulated. And so you explore the possibilities to try to get insight into the solution to that question. Solving CH is a vague question because however you solve it, it involves a new axiom. You're not going to prove it from here. So that would be a slight.
Do you think that's a flaw? Is it a flaw in set theory that there isn't an articulated Holy Grail?
Well, I think there are articulated Holy Grails. grails now. I mean,
or it was a flaw until you identified the Holy Grail.
So that's not being fair now. He knows I love Holy Grail problems.
Yeah, I have insider information. That's true.
It's like a big area of set theory is intermodal theory. Intermodal theory is develop generalizations about with large cardinals. Well, what are you doing? Well, we're trying to build the intermodal for whatever. Well, what do you mean by that? And then, so it's useful to define the problem, and you're quite sure the only way to solve that problem is to develop intermodal theory, whatever that means. That's a Holy Grail problem. And there are very good versions of that for intermodal theory. And it's just, it has a practical effect. A good Holy Grail problem can be understood by the wider community. And so they have some feeling of, oh, you guys are studying that problem. And then hopefully when you solve it, they'll remember, oh, wait, I remember, you guys have been talking about that problem for years. So it focuses attention. So a good Holy Grail problem focuses attention. But if that problem gets solved by means other than what you intend, you have to take that solution. It's not fair to go,
That's right.
oh, that's not what I meant. So I'll give you an example. When I was a graduate student, the problem of building interesting models of set theory where the continuum was large was was a well-studied problem. And now we know why that problem was so difficult. And that's because forcing axioms imply the continuum is L2. So that's an explanation why it was so hard to build interesting models where the continuum was large. But there was a test question, and that was the Borel conjecture. Mm-hmm. So the Borel conjecture is that a set of strong measure zero is countable. And a set of strong measure zero, if given any epsilon sequence, you can cover the set by intervals which shrink according to that sequence. So CH, you easily get a counterexample. So Laver was the first to show the consistency of the Borel conjecture, but his model had the continuum was L2. So people asked, is the Borel conjecture consistent with the continuum large? So I got interested in the problem. I was a graduate student. And it turned out that it wasn't a very good test question. Because if you take Laver's model for the Borel conjecture and add lots of random reals, you preserve the Borel conjecture. So you could easily get models with large continuum and the Borel conjecture without addressing the fundamental issue, which was how do you do countable support iterations of forcing and get the continuum large? Yeah. So that was not a great test question or a Holy Grail question, even though it was much discussed. But for intermodal theory, we have questions which I'm absolutely sure cannot be solved, easily articulated questions, which cannot be solved by any means other than solve the intermodal problem. I'm quite confident of that. So these Holy Grail questions are useful. And, it's good for people outside the community to understand, like, proof theory. Do the proof theory for ZFC. Well, what's the test question?
Yeah.
And I've never heard one articulated. So it's hard to, it's like, well, what do you mean by doing the proof, ordinal analysis or whatever? Well, it's good to have I'm sure there is one. I mean, ordinal analysis can prove equivalences that are otherwise not known. Like, for example, Harrington is equivalent to Goodstein's theorem. Right. That's the equivalence of two arithmetic statements over piano. But it's proof theory that's used to show the equivalence. So presumably, to do you want to see generalizations of that over stronger theories. I don't know.
So earlier there was some discussion about set theory and category theory, and it seems that for especially maybe a lot of current developers of category theory, a lot of the purpose is maybe not to analyze foundational issues, but to provide a language which makes it easy to do investigations in a certain part of math. Do you think it's one of the duties of logic to find foundations that are good for developing other parts of mathematics, even if they're not so good for analyzing foundations itself?
I'm not doing that.
I can.
Go ahead.
I mean, well, I think what people have done in perhaps the very beginning of category theory, but in topos theory, they provided something extremely coherent which fitted the analysis of sheaves and things of this kind over very general situations, not classical spaces or anything like that. And this the language, prior to the introduction of topos theory, was beginning to pervade algebraic geometry, and it was already beginning to show itself as a truly powerful method for obtaining deep new results, for the formulation of new things. I mean, most of the people who were dominating the subject at that time, like Berkeley and Bethonie, just believed topos. It was the most natural thing in the world, when they related it to the kinds of things they were doing. I don't know what Berkeley thought about set theory. His efforts at writing it in the several universes is certainly not very attractive. And I don't suppose Bethonie is really into set theory at all. I mean, for example, he has a quotation that always struck me in the paper, the Weak Conjectures 2, which is a big thing, again, a Fields Medal paper, where, see, one of they're trying to calculate, or they need to calculate for the Weak Conjectures, the size of the absolute values of Frobenius acting on metallic homology. It's a very, very sophisticated material, and at some point you have to embed the p-adic numbers in the complex. Bethonie drew the line at doing that. He said that the axiom choice is abhorrent to him, and at all costs he must avoid this doing this. Of course, it's not that difficult for the purposes he was doing. He do sort of finite approximations, just get little bits of the p-adics, enough for what you're trying to prove at that moment, get them into things. But of course, in fact, Bethonie was right in the sense that in a solidus model, that you simply do not embed the p-adics into the complex. You cannot do it. So I think in that community, by and large, they were not. Axiom choice was not the thing they wanted. They wanted to be much more explicit, do calculations. And I think they developed something entirely natural about sheaf situations of continuously varying structures. And it was a huge number of people came in and worked on it, and even logicians came in, and people like Scott and Foreman looked at it from the standpoint of in some sense, intuitive model theory, or higher order model theory. So I think that was a perfect thing to do. One, I don't think it was implicit in this that this was to be the foundation for all of mathematics. It was some naturally devised thing, ultimately came from Berkeley, I think, which fitted perfectly the kinds of general abstract arguments they were doing by that point. I don't think they ever did anything else. And I think it is, in general, a good idea for people interested in philosophy of mathematics, which I would take to be really understanding how mathematics has evolved and what changes have happened and so on, and how certain ideas have been out of fashion, others have come in, others have maybe achieved too much importance. It's a good idea if people do things like this in other domains, in other parts of mathematics. Something we haven't discussed here, I don't think we have time in any case, I don't know all that much about it. I mean, there's a great deal of talk now about this homotone type theory as a foundation for mathematics, with the alleged advantage over other foundational schemes, that it carries within it the means of giving formalized proofs and verifying complicated arguments, something never claimed for set theory. I don't think anybody would ever imagine that this claim could be justified. I mean, I don't think we have time today, but at some point, the mathematical logic community should discuss this more. I mean, the dominant ideas came from at least one very great mathematician, Berkeley, who was a master, utterly abstract. I would like to see that kind of thing. I don't know what other areas of mathematics need this kind of thing at the moment, but one can hope that there will be valuable new parts of mathematics will reveal themselves and perhaps in connection with other kinds of computability. So for me, it seems the most natural thing in the world to be on the lookout for that, but not with the idea that giving a local foundation for this thing is changing anything about set theory or any other part. Are you in this kind of area at all, or you're not? No. Is there anybody in the audience who works on the homotopy type theory?
I would love to have a super tech. Maybe in 1,000 years it'll be super tech. You write your paper, and then instead of teching it, it'll proof check and fill in all the gaps. And that would be great.
But they do tend to emphasize this aspect of it. There's Hale's sense of emphasize this aspect too, the fact that these big proofs may have errors in them, but even the short proof with errors in it. I think that's exaggerated, but the idea of so there's two things you might want of such a system: that it maybe for the first time allows some kind of general confirmation of the correctness of arguments and full formalizing, but also that it will create new ideas and advance and create new theorems. And it's not so clear that this is any kind of miracle that's coming along with the end of it. It's early days yet. Yeah, that's one of the things I've always felt we've overdone the business about. It's put too much of a burden on set theory to talk of it as the foundation for mathematics. This general language was appropriate at the time when Frege and Russell and so on what was achieved by people was a miracle, and it was probably indispensable for the proper development of things like measure theory and so on at that very time. And it would have been a mistake. It would have been very bad for math if that had not developed. But I don't think.
Well,
do you see set theory as
no,
foundation? You obviously don't.
I don't. I don't see set theory as that kind of foundation for math. I think we've grown up. Yeah. We don't need that kind of foundations for math. That's
What do you mean by that?
Well, I mean, it's the issues that set theory clarified in the early days are well understood now, and those aren't issues anymore. The foundational issues that set theory seems to be addressing, which haven't reached other areas of mathematics yet, are out of the independence results, and that's a different issue. If independence makes its way into classical mathematics like number theory, if a pi02 sentence is independent, then you have a serious issue in trying to figure out whether it's true or not. But we don't really have techniques. I mean, there's one example. It's the biggest gap I know of in terms of what you need to prove something versus what you use to prove it. And it's a really good example where large cardinals basically discovered something about finite algebra. And that it begins in Laver's work on the left distributive algebra. And so left distributive algebra is, you have one operation that's left distributive. And Laver used large cardinals to solve the word problem for the free left distributive algebra on one generator. And then Bethonie came up with a classical proof using braid groups. But out of the large cardinal perspective, something interesting was discovered. And a theorem proved. So it turns out that for every n, there's a unique distributive algebra with 2 to the n elements up to isomorphism. And there's a natural homomorphism. You just do mod 2 to the n mod 2 to the n from an plus 1 to an. So you do it all. And so then you take the inverse limit. And you take that generator. So these are all, singly generated algebras. You take the inverse limit. So some big left distributive algebra. But you look at that generator and you ask, is the subalgebra of the inverse limit generated by that generator the free algebra? Okay? And it comes down to a very concrete question in this sequence of finite algebras. So you assume on the order of a rank to rank, a bit less, that's near the top of the large cardinal hierarchy. The answer is yes, Leibniz theorem. Not known. It's the relevant statement's a pi02 sentence, and not known. And it's known that it can't be done easily, because really what there is associated to this sequence of algebras, there's a function. And it's known it's not primitive recursive. So you have to analyze something that's not primitive recursive. And so it's a whole area. It's called Laver tables and everything. So it's an example where large cardinals, because they give a natural model for the left distributive algebra, discovered a phenomenon down in the finite algebras, proved a theorem there, and it's still not known if you need the strength of the large cardinals. Trying to prove a pi02 sentence, and that pi02 sentence could be equivalent to the one consistency of the theory of large cardinals. There's a theory of large cardinals n huge for each n, and if that theory is one consistent, you get a yes. Well, those are 2 pi02 sentences equivalent. That would be like a fantasy, because that's never happened. But it's a good example where the large cardinal perspective and as a route to discovery, and maybe in the end a very complicated calculation gives the proof without using a number theory or whatever. You can't. It was discovered from large cardinals, and it's that. It's
I think we can have one or two more questions.
Thank you. I have 2 more questions, Professor Woodin. So you said first that meaningfulness of the concept of the universe that demands that questions such as CH have determinate answers. So a question that comes to my mind in this context is, why should we think that we have, or why should we have a determinate conception of the universe? So basically I'm asking about it.
So what I was saying is, if the only justification for the consistency of large cardinals is a conception of a universe of sets in which those large cardinals, something like them, exist, then that seems to demand a resolution to the CH. How can you argue that measurable cardinals are consistent, exist in the universe of sets? So you're saying there, it's clear what's going on, but by the way, we have no idea what's going on down here at the bottom. That somehow feels suspicious to me. That's all. So it's it's the consistency claims of large cardinals falsifiable. How does one account for those? You could just say it's uninteresting, but you could say you could take no position. I mean, there's something really interesting about consistency claims. So, you know, most famous problem in mathematics, all right, the Riemann hypothesis, pi 0, 1 sentence. Take my favorite large cardinal, Woodin cardinal. Consistency of a Woodin cardinal, pi 0, 1. I will declare Woodin cardinals are consistent. Okay, now, what about the Riemann hypothesis? The Millennial Prize Committee had so little confidence in the truth of the Riemann hypothesis that in the initial rules, they would not pay out for a counterexample. So what's going on? I mean, you know, so imagine that someone proved the Riemann hypothesis was independent of PA, or applied con PA, without resolving it. Are they suddenly going to say it's true? So what is it about large cardinals that we're willing to make the claim that the consistency is true? Having verified, we can't prove it. So there's something going on there, and I don't have a clear, I mean, isn't there, I mean, I'm not a number theorist, I'd have to ask Angus, but it seems to me there's overwhelming evidence for the Riemann hypothesis.
Well, actually, I have to write this is the main dark thing on my horizon. I've got to write a Royal Society biographical memoir on Kreisel. These things are usually very long and so on, and his life was both personally and mathematically controversial. So I've been looking back at some of the early papers, which are very difficult. And he was very much interested in the Riemann hypothesis. And in fact, I think he was probably the first person. Turing analyzed the Riemann hypothesis instantly after he got the computable numbers. And Turing, I guess, probably should have by 0, 2 or something like that. Turing, I mean, they were doing the same thing. They were doing constructive complex analysis of the classical complex analysis proofs. Kreisel went further, and he found methods which look, very pedantic, but in fact were taken up by number theorists later. The abstract thing was taken up by Turing and so on. And I studied these carefully and went back and looked at Turing, and it seems pretty clear that Turing, by the end of his life, and he was an expert on these matters, he published many papers on analysis, and he analyzed the Riemann hypothesis. But he, I think, by the end of his life, reached the conclusion that it was almost surely false.
Final question?
It's so beautiful. True, I guess it's the standard thing.
So if you set up a betting market on the Riemann hypothesis, what would the shares be trading at?
There are a lot of people who prove theorems based on the Riemann hypothesis. So I think the prevailing view, I think, is that it's true.
Well, I mean, there is this coherence again. I mean, because you told me just the Riemann hypothesis, you get all these other things about L series and so on, and predictions. It's relevant to Fermat's last year and so on. Related things are relevant. You have a picture of enormous coherence, like that's the set theory. But in fact, there's nothing towards it. You've got this coherent picture, and you spread out all the time, and you get deeper and deeper invitations. Of course, you get these marvelous things of Lischko and so on. They can locate the zeros up to God knows how far, but there's many questions they cannot answer, even low down. I mean, this thing that Kreisel was obsessed with when Littlewood showed that, the number of primes is connected to this logarithmic interval, and one of them dominates the other for as far as one could see at the beginning, and then there's a switch in sign between the Littlewood proved it, first of all, using hypothesis. And I used the argument by contradiction, split into cases. And Kreisel became interested in trying to get some constructive estimates as to where this switchover happens. Over the years, people have got better results, but Kreisel in his latter years, so he only had 2 or 3 years left to live. I mean, almost, certainly weekly, I was given the assignment of contacting Sarnak or some other eminent number theorists, and I spoke to them in detail, and they were interested very much. Sarnak had worked on things like that, as to where they are now in terms, and there was some gigantic bounds such that the changeover happens before that, but they cannot get it down. Even the people who, the guy who did the stuff on the January Goldbach and so on, and I asked him, and he couldn't. They can't get it down. They don't really know enough, even about low down, whatever. I mean, so I think it's slightly illusory. One knows a lot, but in terms of ultimate new theory, there hasn't been that much. And I think Turing's quite explicit that, probably there's something out there.
So that makes the set theorists look foolish, right? We're willing to say these pi01 sentences like large cardinals are true.
Well, but they may be bigger than that. I don't know. Sarnak has some fantastic things about, distribution of primes and the bias in the numbers, things like Chebotarev's theme about equidistribution of the primes of different congruence classes and more complicated things. But in finer detail, there are big differences between there is an equidistribution, but if you look at it more deeply on another scale, there's not. There's a bias in favor of one over the other. And they get hold of these things, so they have tremendously sophisticated methods, but it doesn't get you anywhere near the natural questions about the human hypothesis. Then you have all this stuff on random matrices and predictions about reactions to that. It's a picture, fantastically suggestive, but it doesn't advance the computational side very much.
I still think they should pay off for a counter.
Yeah, I agree. Of course I agree with you. This is crazy.
Well, they may have I haven't looked at the rules in that many days.
No, I do remember Slaman gave a talk on the Riemann hypothesis at one of the ICMs, maybe in Berlin, and he did sort of express, maybe he was on the committee, I don't know, but he made it clear that it was going to be very bad because it was false. And he said it in a sort of disparaging way. They didn't say it wouldn't be mathematics, but there was a clear sense there that, if there is a counter example, don't find it or something like that.
Another one, last one. Why should it be that the large cardinals are a sign of truth in a sense? You said that, for example, E equals L is false because it is incompatible with large cardinals. So why does compatibility with large cardinals, according to you, is a sign of truth?
Well, incompatibility is a sign of falsehood. It would be my view. It seems to me set theory, the conception of the universe of sets, it's all about infinity and having large cardinals. And if you have a framework for V which is incompatible with large cardinals, that seems inconsistent with the founding principles of the conception of the universe of sets. And so you're compelled to reject it. For example, if you assume V is equal to L, you gain nothing except a lack of information. You no longer see the projective sets in their true form. It seems to me absolutely compelling that V is not L. You just wipe out or obscure rich structure theory that's been discovered. So that's why I would say compatibility with large cardinals in some form, is essential. A proposed axiom for something like generalization of V is equal to L, the litmus test for that is it better be compatible with large cardinals, or you have to reject it. So that's all. It's that's set theory is about big sets. So a set theory without big sets is not set theory. And it's an interesting question whether it's kind of like we seem to have a robust conception of the integers, right? Most people agree that arithmetic statements are true or false. Determinacy extends that to second-order number theory. In fact, it's harder to get independence in second-order number theory in the context of determinacy because than to get independence in number theory. So there are examples of arithmetic statements independent from the piano axioms, like pairs Harrington. Those analogs don't exist for PD. It's much, much harder. So now it raises a question. Well, we have a conception of second-order number theory that's robust. Why can't we have a conception of V that's that robust? So immune to forcing, compatible, So is there such a conception of V? How would you make the case that there is? What criteria would have to be satisfied? How could you make the case that there is no such conception? Those are interesting questions. I mean, it can't be a slog up. You understand the power of the integers and the power of the reals and the power of the reals. That's a long way. If there is a robust conception of V, it's just got to be one axiom. And is there such an axiom? And how could you verify that it does provide that conception? Or maybe you can make a case that there can be no such axiom. And how would you make that case? Now, in that latter case, okay, so I'll close with this. I said that consistency traces back to existence. That seems to be the only mechanism we have. Well, if you look at the large cardinal hierarchy in the context of the axiom of choice, it goes up to one level and just stops. The Kuhnen contradiction. And it's a very ad hoc, just runs into a wall. But the axioms go further. Now, the usual view is those axioms are inconsistent. But that's not entirely accurate as far as we know. They just imply the axiom of choice is false. So we have, in the natural language of large cardinals, these axioms which we now know imply the consistency of all the ZFC compatible large cardinal axioms that we have. So we have no basis for the consistency of these supra-large cardinal axioms, which deny the axiom of choice. There's no ZFC candidate that's going to match among those that we know. So if consistency traces back to existence, and these axioms are consistent, does that mean we have to give up the axiom of choice? So there's a serious issue here. Or maybe these axioms are inconsistent outright, and they'll be the first examples of inconsistency in the natural language of large cardinal axioms, where the inconsistency is the result of a deep structural analysis. The point is, without the axiom of choice, the universe is a very difficult thing to analyze. So it could be that these axioms are inconsistent, but they involve really profound insight into the structure of V, because it has to work in a choiceless context. And there's that Hodgkin dichotomy theorem. I said that if you have an extendable cardinal, this is in ZFC, Hod is either very close to V or very far from V, and far from V in a way we cannot do. So the conjecture is that Hod must be close to V. Now that's a ZFC conjecture. If that is provable, in other words, ZFC plus an extendable cardinal implies Hod is close to V, that wipes out the choiceless hierarchy. So a deep structural theorem, Hod must be close to V in ZFC now, with large cardinals, would translate into a ZFC inconsistency result. And if it goes that way, that's a good candidate for a deep inconsistency result in the natural language of large cardinals, pushing back on the idea that if you formulate a large cardinal axiom in terms of elementary embeddings or whatever, in the natural language, and you just stare at it, you'll either see that it's inconsistent right away or it's probably consistent. And it would be a very strong counterexample to that intuition. So that's part of the dichotomy, I think, that set theory faces.
Well, it's always a great experience to be at a forum like this, to listen to leading mathematicians to talk about the subject of mathematics, and in this case, from the foundational point of view and from their own perspective. In my entire career so far, I've only had the chance of attending such forums on very few occasions. I've counted not more than 3 or 4. And today's forum, I think, was intellectually very stimulating, and certainly, I think, personally, I have benefited greatly from this the discussions that took place. And I believe that the audience here, especially the students, young people, I think many years from now, when you reflect, you remember the session today, and it might even have some impact on your intellectual development. So please join me in thanking Professor Woodin, Professor MacIntyre, and Professor Slaman. So that ends the session. Don't forget that tomorrow there's still class to attend. Thank you.